Right now, about 100 meters beneath a vineyard, on the border between France and Switzerland, 27 kilometers of tunnel are sitting in the dark. They are lit and empty, and the magnets lining them are being held colder than deep space, and nothing is moving through them at all. 6 weeks ago, the last protons went around that ring and were steered into a block of graphite, and the largest scientific instrument ever built stopped. 17 years of running. Around $10 billion. One new particle. But the strange part is not the price. That machine was built to settle a question you can state in 6 words. Everyone agrees it did its job, and did it better than it was designed to. And the question is less settled tonight than it was before anyone switched it on. By the end of tonight, you will know exactly what that question was, and exactly why physicists can no longer agree whether it was a question at all. Before we begin, if following one stubborn question this slowly is how you like to fall asleep, a quick like or subscribe really helps the channel grow. It's a small thing for you, and it means a great deal to me. Now, let's begin. On the 27th of June, 2026, the most powerful machine human beings have ever constructed was switched off, and almost nobody noticed. There was no ceremony, there was no final grand experiment, no last dramatic collision staged for the cameras. A beam of protons completed one more circuit of a 27-kilometer ring buried beneath the border between France and Switzerland, and then it was steered sideways, out of the ring, into a block of graphite and steel designed to absorb it harmlessly. The magnets stayed cold. The screens kept updating, and the Large Hadron Collider, which had been running in one form or another since 2009, stopped colliding anything at all. It will not collide anything again for about 4 years. The tunnel is being emptied of hardware. The detectors are being pulled apart and rebuilt from the inside out. Somewhere between now and the early 2030s, the machine will come back as something more powerful, and the people who spent their careers building it will be a little older, and some of them will have retired, and a few of them will not be there at all. Let me take you into the room where it happened, because the strangest thing about that night is how ordinary it looked. It is dark outside the CERN control center, and inside the lighting is the flat white of any office anywhere. 4 clusters of desks, arranged in islands, each one facing a wall of screens. There are coffee cups, there are cables taped to the floor. On the largest display, a single line traces the beam intensity, and it has been almost flat for hours, because a good night here is a night when nothing happens. People are standing behind the chairs rather than sitting in them, which is the only real sign that this is not a normal shift. Somebody is holding a phone up to record. The engineer at the console works through the dump sequence the way she has worked through it 1,000 times before, because it is the same sequence, and the fact that it is the last one does not change a single step of it. The number on the intensity plot drops to 0. It takes less than a heartbeat, and then the line is flat in a different way than it was flat before, and the room makes the sound a room makes when everyone in it exhales at once, and nobody knows whether to clap. That is what the end of the largest scientific experiment in history actually looks like. A number going to 0 on a screen in an ordinary room at an ordinary hour. It is worth knowing what was in the tunnel underneath that room. The ring is 26.7 kilometers around, buried between 45 and 170 meters below farmland, suburbs, and the edge of a lake. Along it sit more than 1,200 superconducting dipole magnets, each one 15 meters long, each one carrying a current of about 11,800 amps. To carry that current without resistance, they have to be held at 1.9 Kelvin, which is colder than deep space. The radiation left over from the Big Bang, filling every cubic meter of the universe, sits at about 2.7 Kelvin. The magnets in that tunnel were colder than the background temperature of the cosmos, continuously, for years at a time, and the cryogenic plant that held them there is the largest refrigerator ever built. Inside the beam pipes, the vacuum was emptier than the space at the surface of the moon, and through that emptiness, protons traveled at 99.9999991% of the speed of light. Here is what that machine accomplished. Over its operating life, it delivered nearly 550 inverse femtobarns of integrated luminosity, which is the unit physicists use to count opportunities. Translated into plain language, it means the machine produced something on the order of 100 million billion proton collisions. The original target was 300 inverse femtobarns. It delivered almost twice that. Oliver Bruning, who directs accelerators and technology at CERN, put the achievement in a comparison that is worth sitting with for a moment. That single machine produced roughly 50 times the total combined dataset of every hadron collider that had ever operated anywhere on Earth before it switched on. Not 50% more, 50 times. During its most recent run alone, each of the two general-purpose detectors, Atlas and CMS, recorded proton collisions numbering about 4 times 10 to the 16th. That is 40,000 million collisions in each of two machines in 4 years. The data generated over the full program is measured in exabytes and is distributed across a computing grid that spans dozens of countries. The analysis of what was collected will continue well into the 2030s. The dataset will outlive the machine that made it by more than a decade. And in 17 years of operation, out of all of that, the Large Hadron Collider found exactly one thing. It found the Higgs boson. On the 4th of July 2012, 2 independent teams announced, within an hour of each other, that they had seen a new particle at about 125 giga-electron volts. It was real, it was confirmed, and it was the last missing piece of a theory that had been under construction since the 1960s. That discovery is genuinely one of the great intellectual achievements of our species, and I do not want to diminish it for a second. But it was not the reason the machine was built, or rather, it was not the only reason, and by most accounts it was not even the main one. Finding the Higgs boson completed a theory. Completing that theory was never the objective. The objective was to break it. Because here is the thing about the theory the Higgs boson completed. It is the most precisely tested description of nature that human beings have ever written down. It predicts some quantities to 11 decimal places and gets them right. And it is also, everyone agrees, unquestionably incomplete. It contains no description of gravity at all. It has nothing to say about dark matter, which outweighs ordinary matter in this universe by a factor of more than 5. It cannot explain why there is any matter here, rather than equal amounts of matter and antimatter that annihilated long ago and left nothing behind. And it contains at least 19 numbers that nobody can derive from anything, numbers that simply have to be measured and then written into the equations by hand. The Large Hadron Collider was built, in very large part, to find out what lies beyond that theory. Physicists had specific, well-motivated, quantitative reasons to expect that the answer would be sitting right there in the energy range the machine was designed to reach. Not a vague hope, a calculation. The machine reached that energy range. It reached it, and then exceeded its own performance targets by a factor of nearly 2. It looked, with 2 independent detectors, for 17 years. It found one particle and nothing else. Now, I want to be very careful here, because there is a lazy version of this story that gets told a lot, and the lazy version is wrong. The lazy version says that the collider failed, or that the money was wasted, or that physicists were fools. None of those things are true, and by the end of tonight I think you will see clearly why none of them are true. What actually happened is stranger and much more interesting than failure, and it has left the field in a position it has never occupied before in its entire history. Because the question that machine was built to answer was not just any question. By almost any measure you choose, It is the single most expensive question ever asked by human beings. And it does not have an answer tonight. Not a partial answer, not a promising lead. It does not have an answer, and this is the part that took me a long time to understand. The people who asked it can no longer agree on whether it was a question at all. So before we can talk about why there is no answer, we have to talk about what the question actually was, and what it actually cost to ask it. And the cost is the easier part, so let us start there. Nobody can tell you exactly what the Large Hadron Collider cost, and the reason why is itself revealing. CERN's own accounting, published in January 2010, puts the accelerator at approximately 4.6 billion Swiss francs, with a further 1.16 billion Swiss francs for CERN's contribution to the experiments. Those are the official numbers, and they are accurate as far as they go, but they leave out a great deal. They leave out the detector components paid for directly by universities and national funding agencies in dozens of countries, contributions that never passed through CERN's books at all. They leave out 17 years of electricity, maintenance, salaries, and cryogenics. They leave out the computing grid, and they leave out the single largest hidden subsidy in the entire project, which is the tunnel itself. The Large Hadron Collider did not dig its own tunnel. It moved into one. Between 1983 and 1988, CERN excavated a 27-kilometer ring for a different machine entirely, an electron-positron collider called LEP, which ran until the year 2000 and was then taken apart to make room. That excavation was one of the largest civil engineering projects in Europe at the time, and inheriting it saved the new project something on the order of 1 billion francs. If you want to know why the collider is where it is, in that particular loop, under that particular stretch of countryside, the answer is that a previous generation of physicists had already paid for the whole. Add everything together, draw the boundary generously, and the figure most commonly quoted for the full program is somewhere around 7.5 billion euros, or roughly $10 billion, depending on the exchange rate and on which costs you decide to count. There is no single official $10 billion receipt anywhere. The number is a reasonable summary of a project whose true cost is spread across dozens of national budgets over 3 decades. The detectors are their own answer to the question of where the money goes. Atlas is 46 meters long and 25 meters across, weighs about 7,000 tons, and sits in a cavern large enough to hold a cathedral. CMS is physically smaller and considerably heavier, at roughly 14,000 tons, and contains more iron than the Eiffel Tower. The superconducting solenoid at the heart of CMS stores about 2.6 gigajoules of energy in its magnetic field, which is comparable to half a ton of high explosive, and discharging it safely takes several minutes. These are not instruments in the sense that a telescope is an instrument. They are buildings that happen to take photographs, and each of them was assembled underground, piece by piece, by collaborations of thousands of people from institutions that in many cases had never worked together before. Machines like this also break. 9 days after the first beam circulated in September 2008, a faulty electrical connection between 2 magnets caused what is called a quench, in which a superconducting magnet abruptly stops superconducting and dumps its stored energy as heat. 6 tons of liquid helium vented into the tunnel. 53 magnets were damaged. The repair was reported at around $29 million, and the machine did not run again for more than a year. That incident is a useful correction to the idea that any of this was routine. The collider spent its first year and a half being difficult, and then it spent 17 years being extraordinary. It also went over budget. The original construction allocation was 2.6 billion Swiss francs. The final accelerator cost came in around 850 million francs above that, and CERN's member states absorbed the overrun by restructuring the payment schedule in the early 2000s. This is not scandalous. It is what happens when you build something that has never existed before. But it is worth remembering, because 13 years earlier, on the other side of the Atlantic, a cost overrun on a very similar project had ended very differently. I want to take you to a field in Texas. It is the autumn of 1993, outside a town called Waxahachie, about 30 miles south of Dallas. The land is flat, and the soil is a soft pale limestone called Austin chalk, which is exactly the sort of rock you want if you are going to bore a very long tunnel very quickly. 17 shafts have been sunk into it. 14 miles of tunnel have already been cut. Down there in the dark, the boring machines sit in a passage wide enough to drive a car through, cut for a collider that was designed to run at 40 trillion electron volts, nearly 3 times the energy the Large Hadron Collider would eventually reach. Above ground, there are laboratory buildings, magnet test facilities, a workforce of thousands. $2 billion have already been spent. On the 19th of October, in a building 250 miles from anyone who has ever operated a boring machine, the United States House of Representatives votes 264 to 159 to stop paying for it. The President signs the appropriations bill on the 30th, and that is the end of it. The estimate to shut the project down cleanly and seal the shafts is another $1 billion, which means the taxpayer pays $3 billion for 14 miles of empty tunnel and no physics whatsoever. The ring, had it ever been finished, would have been 87 kilometers around, more than 3 times the circumference of the machine under Geneva, and it would have held that title for the next half-century. The tunnel is still there. It is still under that farmland tonight, unfinished, most of it flooded, occasionally rented out for storage. It is the largest physical monument in the world to the possibility that a civilization can start asking a question and then simply stop. The superconducting super collider died for a combination of reasons. The cost estimate had climbed past $10 billion. Foreign contributions never materialized at the levels promised, and the Cold War had ended, taking with it a great deal of the political appetite for very large physics. But the practical consequence is easy to state. When the American machine was cancelled, the European machine became the only one. Every question that generation of physicists wanted to ask about the fundamental structure of matter now had to be routed through a single ring under a single border, and if that ring did not find the answer, there was no second instrument anywhere on Earth that could check. So that is the price tag. $10 billion, give or take, plus $3 billion more, in Texas for the tunnel that never became anything, plus 17 years, plus the working lives of something like 10,000 physicists and engineers across more than 100 countries. Whatever the question was, it was not asked cheaply. But I want to push on the word expensive for a moment, because money is the least interesting part of this. Consider what else was spent. The theoretical work motivating these searches ran for 4 decades. Tens of thousands of papers were written. Entire academic careers were built inside a framework whose central prediction was that something would show up at the energy the collider was designed to reach. Graduate students chose thesis topics on that basis. Faculty positions were created and filled on that basis. Experiments in deep underground laboratories, in mines and under mountains from South Dakota to Italy to China, were designed and funded to catch the same expected physics coming at us from a different direction. When you count all of that, the collider is not the expense. The collider is the receipt. And I want to be very clear that the people who spent all of this were not gambling. That is the part I most want you to understand before we go any further. They were not throwing money at a hunch. They had a specific argument, worked out over decades, that told them roughly what energy to build for, and roughly what they should expect to find when they got there. That argument had been used before, 4 separate times, and every previous time it had been used, it had worked. It had predicted particles that were subsequently discovered, sometimes to within a factor of 2 of the predicted mass. The question they were asking with all of that money was, on its face, almost absurdly simple. It is not a question about black holes or extra dimensions or the beginning of time. You can state it in 6 words, and I am going to state it now, so that you have it, even though I am not going to tell you its name until later, and I am not going to be able to tell you the answer at all. Here it is. Why is the Higgs boson light? That is it. That is the $10 billion question. And to see why anyone would spend $10 billion on it, we first have to look properly at the one thing the machine actually found, and at the number that came with it. The 4th of July 2012 was the best day that field has had in 50 years. 2 collaborations presented that morning in the main auditorium at CERN, one after the other. People had queued overnight to get seats. Peter Higgs was in the room, 83 years old, watching an experiment confirm something he had written down in 1964, in a paper that a journal had initially rejected, on the grounds that it was of no obvious relevance to physics. Atlas and CMS had not been permitted to see each other's results beforehand. The 2 collaborations are deliberately kept independent, precisely so that neither can talk itself into agreeing with the other. Both reported a new particle at about 125 giga-electron-volts. Both cleared the 5 standard deviation threshold that particle physics requires before it will use the word discovery. Both saw it in more than one decay channel. Higgs was seen wiping his eyes. Englert and Higgs shared the Nobel Prize the following year. Robert Brout, who had published the same idea a few weeks earlier than Higgs, in 1964, had died in 2011 and could not share it. I am not going to re-explain the Higgs mechanism tonight, partly because we have spent a long evening on the origin of mass before, and I do not want to repeat myself, and partly because for tonight's purposes, the mechanism is not the point. What matters tonight is much simpler. What matters is the number. The particle's mass is now measured at approximately 125.11 giga-electron-volts, with an uncertainty of about 11/100ths of a giga-electron-volt. That is a precision of roughly 0.09% on a particle that exists for about 1.6 times 10 to the minus 22 seconds before it falls apart. Nobody has ever seen a Higgs boson. What they see is the debris, 2 photons flying apart back to back, or 4 charged leptons, and they reconstruct backwards to the thing that must have been there. From that debris, sifted out of 100 million billion collisions, they have pinned the mass of a particle that never survives long enough to travel the width of an atomic nucleus. And with that measurement, the standard model of particle physics was complete. Every particle it predicted had been observed. The last box was ticked. I want to sit with how strange it is that this was a problem. The standard model is, by a wide margin, the most successful physical theory ever constructed. It describes the electromagnetic force, the strong nuclear force, and the weak nuclear force, and the 17 fundamental particles that make up everything you have ever touched. It has been tested to 11 decimal places in some quantities, and it has never once been caught out. Not once, in 50 years, has any experiment produced a confirmed result that contradicts it. If you wanted to name the single greatest achievement of 20th century physics, you would have a strong case for this one. And every physicist who works on it will tell you, without hesitation, that it is wrong. Not wrong in the sense of mistaken, wrong in the sense of unfinished, in a way that is not a matter of opinion. Start with gravity. The standard model contains no description of gravity at all. It is not that gravity is included approximately, or included in a way that breaks down at extreme energies. It is simply absent. The theory that describes the very small and the theory that describes the very large have never been made to speak to each other, and every attempt so far has produced nonsense at high energies. Then there is dark matter. Something is out there with mass, something that bends light and holds galaxies together and shapes the pattern of the oldest light in the universe, and it outweighs everything the Standard Model describes by a factor of more than 5. The current best accounting gives roughly 5% of the universe's energy budget to ordinary matter, about 27% to dark matter, and about 68% to dark energy. The most successful theory ever written describes the 5%. It has nothing whatsoever to say about the rest. Then there is the fact that you exist. In the first instance after the Big Bang, matter and antimatter should have been produced in almost exactly equal quantities, and they should have found each other and annihilated, leaving a universe of light and nothing else. Instead, some tiny asymmetry, roughly one extra particle of matter for every billion pairs, survived the annihilation, and everything made of atoms is built from the leftovers. The Standard Model contains a mechanism that produces an asymmetry of this kind, and when you calculate the size of the effect, it comes out far too small. By many orders of magnitude, something else has to be happening, and nobody knows what. There is also one place where the Standard Model has already been broken, and it is worth naming because it shows what a genuine crack looks like. The original theory required neutrinos to be exactly massless. In 1998, the Super Kamiokande experiment in Japan showed that neutrinos change type as they travel, and in 2001 and 2002, the Sudbury Neutrino Observatory in Canada confirmed it from a different angle. Changing type is only possible if neutrinos have mass. Takaaki Kajita and Arthur MacDonald shared the Nobel Prize for it in 2015. So the Standard Model has been falsified, once, by an experiment in a mine, and the correction was absorbed by adding parameters rather than by rebuilding the theory. It was a crack, not a collapse. What physicists wanted from the collider was a collapse. And then there are the numbers. The Standard Model has at least 19 free parameters, around 26 once you include the masses of neutrinos, which the original theory did not even allow to have any. A free parameter is a number the theory cannot predict. You measure it, you write it into the equation by hand, and from then on the theory works beautifully. 9 of them are particle masses, 3 are mixing angles, 3 are the strengths of the 3 forces. Nobody knows where any of them come from. So the situation on the 5th of July 2012 was this. The most successful theory in the history of science had just been completed, and completing it had confirmed that it could not be the final answer. It was like finishing a magnificent building and discovering that the blueprint had no foundations drawn on it, and that the building had been standing anyway, for reasons nobody could explain. The collider had done what it was asked to do, but the physicists in that auditorium had not spent 30 years and $10 billion to tick the last box on a theory they already knew was incomplete. They had come for the next theory. They had come, specifically, for the thing that they had very good reason to believe was waiting just past the Higgs boson, at an energy the machine could reach. And when I say very good reason, I mean it. This is the part of the story that almost never gets told properly, and it is where we are going next, because it starts with something wrong about that number. Not wrong in the sense of measured incorrectly. The measurement is excellent. Wrong in the sense that, according to everything physicists understood about how quantum fields work, 125 giga-electron-volts should have been impossible. There is a fact about quantum field theory that almost never makes it into popular accounts, and once you have it, a great deal of modern physics suddenly makes sense. The mass of a particle is not a number that somebody writes into the equations. Or rather, somebody does write a number into the equations, but that number is not the mass you measure. The mass you measure is that starting number plus the effect of everything the particle does while it is being itself. Let me make that concrete. An electron sitting apparently alone in empty space is not alone and is not sitting still. It is constantly emitting and reabsorbing photons. It is briefly turning into an electron and a photon, and then back into an electron. It is momentarily becoming an electron plus an electron-positron pair, which then annihilates back down. Every one of those excursions carries energy, and energy has mass, and so every one of those excursions contributes something to the mass you actually weigh when you put the electron on a scale. What you measure is never the bare parameter. What you measure is the parameter plus the sum of every possible thing that can happen. Now here is where it gets uncomfortable. When you try to add up those contributions, you have to decide how energetic the excursions are allowed to be. In principle, the electron can borrow arbitrarily large amounts of energy for arbitrarily short times, and if you let that go to infinity, the sum diverges. So physicists impose a cutoff, an energy scale above which they admit they do not know what the theory looks like, because presumably something new takes over up there. The natural place to put that cutoff, if you believe your theory holds as far as it possibly can, is the Planck scale, at about 10 to the 19th giga-electron-volts. That is where gravity becomes as strong as the other forces, and where everyone agrees the current description must break down. For the electron, this is fine. The corrections grow only logarithmically with the cutoff, which means that even if you run the theory all the way up to the Planck scale, 16 orders of magnitude above anything we can produce, the correction to the electron's mass is a modest multiple of the mass itself. Nothing dramatic happens. And there is a reason for that gentleness, a reason with a name. It is called chiral symmetry. If you set the electron's mass to 0, the theory acquires an extra symmetry it did not have before. Left-handed and right-handed electrons become completely independent of each other and stop mixing. And here is the crucial structural fact. If setting a parameter to 0 makes a theory more symmetric, then that parameter is protected. The quantum corrections cannot generate it out of nothing, because generating it would violate the symmetry that appears when it vanishes. A small electron mass stays small. It is not a coincidence. It is enforced. Victor Weisskopf worked out the essential structure of this in 1939. In the classical picture, the energy stored in an electron's own electric field grows without limit as you shrink the electron toward a point, which makes a point electron infinitely heavy. Weisskopf showed that once you include the positron, antimatter, discovered by Carl Anderson only 7 years earlier, the divergence softens dramatically. The runaway becomes a crawl. A new particle had turned an impossible number into a manageable one. Hold on to that. It is going to matter enormously in about 20 minutes. Now apply all of this to the Higgs boson, and everything goes wrong. The Higgs is the only elementary scalar particle in the Standard Model. Scalar means it has no spin, no intrinsic handedness, no orientation, nothing to distinguish a left-handed version from a right-handed one, and that means there is no chiral symmetry to protect it. Setting the Higgs mass to 0 does not make the theory more symmetric. It just makes the Higgs mass 0. The parameter is naked. The consequence is severe. For a scalar, the quantum corrections to the square of the mass do not grow logarithmically with the cutoff. They grow with the square of the cutoff. If the cutoff is the Planck scale, then each individual contribution to the Higgs mass squared is of order the Planck scale squared. Compare that to the observed value, 125 gigaelectronvolts against 10 to the 19th gigaelectronvolts is a ratio of about 10 to the minus 17. Square it, because we are working with masses squared, and you get 10 to the minus 34. I want you to see what that actually means, so let me take you inside the calculation. Imagine you could stand in the vacuum and watch the mass of the Higgs boson being assembled. Contributions arrive one after another. The top quark loop arrives, and it is negative, and it is enormous, a number with roughly 34 zeros more than the answer. The gauge boson loops arrive, and they are positive, and they are enormous. The Higgs field's interaction with itself arrives. Each of these is not a small adjustment to a mass. Each of them is, on its own, catastrophically larger than the thing being calculated. You watch them stack up, plus something with 34 extra zeros, minus something with 34 extra zeros, plus, minus, plus. And then you watch them cancel. Not approximately. The first digit cancels, and the second, and the 10th, and the 20th, and the 30th. 34 decimal places of cancellation, digit after digit after digit, and then, right at the very bottom, in what would be a rounding error on a rounding error, a residue is left over. And that residue is 125 giga-electron-volts. That leftover crumb at the bottom of a 34-place cancellation is the number that sets the size of every atom in your body. Move it, and chemistry stops. Make it a little larger, and atoms shrink, and nuclei stop holding together. Make it a little smaller, or push it the other way through zero, and there is no electroweak symmetry breaking at all, and there are no atoms to discuss. One detail in that cancellation is worth pulling out, because it tells you where physicists expected the solution to come from. The largest single contribution comes from the top quark, which is by a wide margin the heaviest known elementary particle at about 173 giga-electron-volts, roughly the mass of an entire gold atom, packed into something with no measurable size. The top quark couples to the Higgs field more strongly than anything else does, and so it dominates the corrections, and its contribution is negative. Whatever cancels it has to be something that contributes positively and couples just as strongly. That single observation is the seed of nearly every proposed solution of the last 40 years. Numbers of that size stop meaning anything, so let me put 10 to the 34 into something you can hold. Suppose you took two mountains, weighed each of them to the last atom, and subtracted one weight from the other. 10 to the 34 is roughly the ratio between the mass of a mountain range and the mass of a single grain of sand. The calculation of the Higgs mass is that subtraction, two quantities the size of mountains, differing by exactly 1 grain of sand, and the grain of sand is the part that determines whether matter can exist. Nobody weighed those mountains. Nobody arranged for them to differ by a grain. They simply do. That is what people mean when they say the Higgs mass is balanced on a knife edge. And I want to be precise about what the problem is, because it is easy to state it wrongly. The problem is not that the cancellation is impossible. It is perfectly possible. Nothing in physics forbids two enormous numbers from cancelling to 34 decimal places. The equations are entirely happy. If you simply choose the bare parameter to have exactly the right value, out to 34 digits, you get the observed answer and everything works. The problem is that nothing in the theory explains why the bare parameter would have that value. The bare parameter lives at the Planck scale, in whatever the true fundamental description turns out to be. The quantum corrections come from the physics of the electroweak scale, 17 orders of magnitude below. Those two things have no reason to know about each other, and yet they appear to have agreed, to 34 decimal places, on a value. To feel the full weight of this, you need one more idea, and it belongs to Kenneth Wilson, who reshaped how physicists think about scales in the early 1970s. Wilson's insight is that physics organizes itself into layers, and that each layer is largely deaf to the layer above it. You do not need to know about quarks to do chemistry. You do not need to know about atoms to do fluid dynamics. When you describe water flowing through a pipe, the details of nuclear physics do not intrude. They get absorbed into a handful of numbers like density and viscosity, and then they are gone. This is not a convenience. It is the reason science is possible at all. If every calculation about a river required knowing the physics at the Planck scale first, nobody could ever have got started. That principle is exactly what the Higgs mass appears to violate. Here is a quantity at the electroweak scale whose observed value depends, apparently delicately, on a conspiracy with physics 17 orders of magnitude above it. The layers are not deaf to each other. They are in exquisite, unexplained agreement. And that offends not a matter of taste, but the working assumption that has underwritten every successful calculation in physics for a century. I should say, in fairness, that the Higgs is not even the worst offender. The energy of empty space, the cosmological constant, the thing driving the accelerating expansion of the universe, is measured to be a small positive number, and the naive quantum field theory estimate of what it should be exceeds the measured value by as much as 120 orders of magnitude. That is a far more extreme discrepancy, and it is often called the worst prediction in the history of physics. But nobody knows how to build a machine that addresses it. The Higgs was different. The Higgs looked solvable. The energy scale involved was one that human beings could actually reach, and that is precisely why it became the question worth $10 billion. Physicists have a word for a number like that. They do not call it wrong, they call it unnatural. That word is going to carry the entire rest of this story, and it means something much more specific than it sounds. So let us go and get it. The word is naturalness, and it has one of the most interesting histories of any idea in modern physics, because it is the only major principle in the field that was never tested and never derived. It was agreed upon. The sharpest formulation belongs to Gerard Hooft, the Dutch theorist, who had already shared in solving one of the hardest technical problems of the century by showing that the electroweak theory could be made to give finite answers. In 1980, lecturing at a summer school in Cargese, on the coast of Corsica, he wrote down a criterion that has been quoted ever since. A parameter is naturally small, he said, if setting it to 0 increases the symmetry of the theory. Read that again slowly, because it is doing a lot of work. It is not saying that small numbers are suspicious. It is saying something much more precise. A small number is fine, unremarkable, requiring no explanation, provided there is a symmetry that appears when it vanishes. If such a symmetry exists, the smallness is protected and self-consistent, and you can stop worrying about it. If no such symmetry exists, then the smallness is a brute fact that the theory has to be told about, and you should worry. By that criterion, the electron's mass is entirely natural. It is about a millionth of the W boson's mass, which sounds extreme, and nobody has ever lost a night's sleep over it, because chiral symmetry is standing behind it. The Higgs mass is unnatural. Nothing stands behind it. The idea did not arrive from nowhere. Leonard Susskind had laid out the physical version of the argument a year earlier, in a 1979 paper on symmetry breaking in the electroweak theory, and he was explicit that he was following Kenneth Wilson, who had emphasized that elementary scalar fields were unnatural in exactly this sense. Martinus Veltman made the same point independently in 1981 in a paper with a title that captures the whole issue, the infrared-ultraviolet connection. The connection is the problem. The low-energy world and the high-energy world are not supposed to be talking to each other this closely. Eldad Gildener had described the hierarchy explicitly in 1976. Within a few years, a loose intuition had hardened into a research program. Now I want to stop and say something plainly, because everything that comes later depends on it, and because it is the part that tends to get skipped. Naturalness is not a law of physics. It is not a conservation law. It is not a symmetry principle, in the sense that gauge invariance is a symmetry principle. There is no experiment, anywhere, ever, that has tested it. There is no theorem that requires the universe to obey it. It is a criterion for judgment, a rule for deciding which numbers demand an explanation and which numbers are just numbers. And a rule for deciding what needs explaining is a very different kind of thing from a statement about how the world behaves. Physicists did try to make it quantitative, which is a revealing thing to attempt. In 1988, Riccardo Barbieri and Gian Giudice introduced a measure of fine-tuning that asks a simple question. If you nudge one of the fundamental parameters by 1%, how much does the electroweak scale move? If it moves by 1%, the theory is robust. If it moves by 1,000%, the observed value is perched on a knife edge with respect to that parameter, and the theory is tuned. The measure gave the field a number to argue about, and arguing about it became a small industry. But notice what the measure does not do. It does not tell you how much tuning is too much. Is a tuning of 1 part in 10 acceptable? 1 part in 100? 1 part in 1,000? There is no principled answer, and there never has been. The threshold has always been a matter of taste, and as the exclusion limits climbed through the 2010s, the threshold that theorists were willing to describe as acceptable climbed with them. Consider what it would mean to test it. To test a physical law, you make a prediction and check it. But naturalness does not predict a value for anything. It predicts that a certain kind of value would be surprising, and that surprise should be resolved by the existence of something else. You cannot measure surprisingness. You can only measure whether the something else turned up. It is worth knowing that some of the people most responsible for the idea grew uneasy about it. Kenneth Wilson, whose framework underpins the whole argument, wrote in a reflection published in 2004 that his earlier claim about scalar masses requiring fine-tuning had been a mistake, and that he regretted having stated it as forcefully as he did. Gian Giudice, who by then was head of CERN's theory department, wrote an essay in 2008 called Naturally Speaking, which remains the standard account of the criterion from the inside, and he was careful to frame naturalness as a research strategy rather than a principle of nature. The people closest to the idea generally knew what it was. What happened is what usually happens when a strategy works repeatedly. The qualifications wear off in transmission, and by the time an idea reaches the textbooks and the press releases, a useful heuristic has quietly been promoted to a fact about the universe. And I want to be scrupulous here, because it would be very easy to make this sound like a foolish thing for a serious field to have believed, and that would be badly unfair. Naturalness was not adopted because it was elegant, or because it was fashionable, or because a few charismatic people pushed it. It was adopted because it had the single best track record of any heuristic in 20th century physics. It had been applied 4 separate times to 4 separate unnatural numbers, and 4 times out of 4 it had led directly to the discovery of a new particle, sometimes with the mass predicted in advance to within a factor of 2. Naturalness was also never applied only to the Higgs, which is part of why it felt like a principle rather than a preference. Quantum chromodynamics, the theory of the strong force, contains a parameter, usually called theta, which could in principle take any value between 0 and 2 pi. If it were not extremely small, the neutron would have an electric dipole moment, a slight separation of positive and negative charge along its axis, that experiments would have detected decades ago. Measurements constrain theta to be smaller than about 10 to the minus 10. There is no symmetry in the standard model that forces it to be that small. It is the same shape of problem as the Higgs, one theory over, and it produced the same response. In 1977, Roberto Pecce and Helen Quinn proposed a new symmetry to explain it, and Frank Wilczek and Steven Weinberg independently noted that breaking that symmetry would produce a new particle. That particle is the axion. It is still being searched for today, and it is now also one of the leading dark matter candidates. So the criterion was not a one-off applied to a single awkward number. It was the field's general method for turning an uncomfortable measurement into a specific experimental target. We are going to walk through all 4, because you cannot understand the confidence without them. But before we do, I want to name the thing that naturalness was invented to rule out, because it is going to come back. The Higgs sits at around 100 gigaelectron volts. The Planck scale sits at 10 to the 19th. Between them lies a stretch of 16 orders of magnitude, a factor of 10,000 million of unexplored energy. If naturalness is right, that stretch cannot be empty. Something has to be in there, and it has to be near the bottom end, close to the Higgs, because the closer it sits, the less cancellation is required. If naturalness is wrong, then that entire span could contain nothing whatsoever. No particles, no new forces, no structure of any kind. 16 orders of magnitude of nothing. Physicists gave that possibility a name in advance, and the name tells you exactly how they felt about it. They called it the desert. The desert was the nightmare. It was the outcome nobody wanted to plan for, because if the desert is real, then there is no signpost anywhere between here and the Planck scale. And the only way to find out what the fundamental theory looks like is to build a machine 16 orders of magnitude more powerful than the one under Geneva, which is not a funding problem. It is a physical impossibility for a civilization on a planet this size. A collider that reached the Planck scale, built with anything resembling current magnet technology, would need to be roughly the size of the solar system. So the stakes were never merely which theory is correct. The stakes were whether fundamental physics, as an experimental science, has anywhere left to go. If something sits at the TeV scale, the field has a future full of instruments and discoveries. If the desert is real, the field's ability to interrogate nature directly may already have ended, and nobody would know until they had looked. That is what was riding on the collider. Not a particle, a question about whether the method still works. And when the machine switched on in 2008, the overwhelming expectation, stated in review articles and grant applications and public lectures and textbooks, was that the desert was not real and that the signpost was there. Not because anyone was being naive, but because 4 times before, when physics had found a number balanced on a knife edge, there had been something underneath holding it up. Let me show you those 4 times. Because once you have seen them, the confidence stops looking like arrogance and starts looking like the most reasonable inference available. The first time was the electron, and we have already met it, but it is worth returning to now that you know what to look for. In the classical picture, an electron carries an electric field, and that field contains energy, and the energy grows without limit as you shrink the electron toward a point. Treat the electron as genuinely point-like, and its electromagnetic mass comes out infinite. This was a real crisis in the 1920s and 30s, not a technicality. The electron was the best understood particle in physics, and its mass was a catastrophe. Victor Weisskopf published the resolution in 1939. Once you include the positron in the calculation, once the theory knows about antimatter, the divergence collapses from linear to logarithmic. The physical reason is that the vacuum around an electron is not empty. It is full of virtual electron-positron pairs that partially screen the charge, and the screening softens the runaway. A number that had looked impossible became merely large, and the thing that fixed it was a particle Carl Anderson had photographed in a cloud chamber only 7 years earlier, and which almost nobody had expected to exist. That is the pattern. An unnatural number is a message, and the message names a particle. The second time was the pion. There are 2 kinds of pion relevant here. The electrically charged one, at about 139.57 mega-electron-volts, and the neutral one, at about 134.98. The difference is small, a little under 5 mega-electron-volts, and the natural explanation is that the charged pion carries an electric field and the neutral one does not, so the difference should be electromagnetic self-energy. But when you calculate that self-energy naively, it diverges, exactly as the electrons did. The integral runs away. What cuts it off is the rho meson, at about 775 mega-electron-volts. The rho contributes with the opposite sign and tames the integral, and when you put its mass in, The calculated pion mass difference comes out close to the measured one. Once again, an unnatural number had pointed at a particle, and the particle was there. The third time is the one I really want to tell you about, because it is as clean a piece of scientific reasoning as I know, and because it is the memory that a whole generation of physicists carried with them into the tunnel under Geneva. In the 1960s, physics knew about 3 quarks: up, down, and strange. That was the model, and it worked well. But there was a problem with kaons, particles containing a strange quark. And the problem was that certain decays simply did not happen often enough. A neutral kaon should sometimes decay into 2 muons. Calculate the rate with 3 quarks, and you get a number. Measure the rate, and it is smaller by a factor of thousands. There was a second, related problem. The mass difference between the 2 neutral kaon states, the long-lived and the short-lived one, was also far smaller than the 3-quark calculation allowed. In 1970, Sheldon Glashow, John Ilopoulos, and Luciano Maiani looked at that suppression and asked the naturalness question. Not why is this number small, but what would have to exist for this number to be small automatically? And they found the answer. If there were a 4th quark, it would introduce an additional quantum process, another way for the decay to proceed, and that process would enter with the opposite sign. The 2 contributions would cancel, almost exactly, and the cancellation would be enforced by structure rather than by coincidence. Then they went further, and this is the part that matters, because the cancellation would only be exact if the new quark had the same mass as the one it was pairing with. The residual size of the effect tells you how heavy the new quark must be. They could read the mass off the measured kaon mass splitting. They predicted not only that a 4th quark existed, but roughly how heavy it was. In November 1974, 2 groups found it on the same weekend. Burton Richter's team at Stanford, working with an electron-positron collider, saw a sharp resonance. Samuel Ting's team at Brookhaven, using a completely different technique, with a proton beam, saw the same thing. Ting had been sitting on his result for weeks, checking it. Richter's group found theirs by scanning through energies and watching the count rate leap by a factor of 100 in a narrow window. The 2 teams learned of each other's results within days and published back to back. Ting called the particle J. Richter called it psi. It has been called the J-psi ever since, because neither community would give way. Its mass is 3.097 giga-electronvolts, and it is a bound state of a charm quark and its antiquark. Richter and Ting shared the Nobel Prize 2 years later. I want you to feel what that was like, because I think it explains everything that followed. 3 theorists looked at a number that was too small. They concluded that a particle nobody had ever seen must exist in order to make it small. They estimated its mass from the size of the discrepancy, and 4 years later, 2 experiments on opposite sides of a continent using entirely different methods found it, approximately where the arithmetic said it would be. Nobody stumbled onto it. Nobody got lucky. The reasoning ran forward from a suspicious number to a specific physical object, and the object was there, waiting. The weeks that followed have their own name in the field. Physicists call it the November Revolution, and the word is not an exaggeration. Before that November, the quark model was one respectable idea among several, and a substantial number of serious people did not believe quarks were physically real objects at all, rather than a bookkeeping convenience. The J-psi is extraordinarily narrow, meaning it lives far longer than a particle of its mass has any right to, and explaining that narrowness required exactly the property that had been proposed a year earlier for the strong force, that quarks interact more weakly the closer together they are. Within about 2 years, the entire community had reorganized around the picture we now call the Standard Model. One prediction, confirmed, converted a contested framework into the foundation of a field. If you were a young physicist in 1974, that is what you learned about how the world works. You learned that when a number looks tuned, the universe is telling you something, and that if you listen carefully enough, you can work out what. That lesson was not superstition. It was the single most successful move available in the field, and the people who made it were rewarded with a Nobel Prize and, more importantly, with the knowledge that the method was sound. There is a fifth case sometimes added to the list, and it is worth a sentence because it shows how ordinary this style of reasoning had become. When the bottom quark was discovered at Fermilab in 1977, the structure of the theory immediately demanded a partner for it, because quarks in this framework come in pairs. Nobody knew how heavy that partner would be, and the search took 18 years and a machine that did not exist in 1977. The top quark was finally observed in 1995 at about 173 giga-electronvolts, far heavier than most people had guessed. But the point is that nobody ever seriously doubted it was there. The theory's internal logic said a partner was required, and the field spent 18 years and a great deal of money on the strength of that logic, and the logic was right. The fourth time was the weak force itself. Enrico Fermi's original 1934 theory of beta decay treats the interaction as happening at a single point, with four particles meeting and exchanging identity. It is a beautiful theory, and it describes low-energy radioactive decay superbly. It also becomes nonsense at high energy. The probability of an interaction grows with energy until, somewhere a few hundred giga-electron volts up, it exceeds 100%, which is not a thing a probability is allowed to do. That breakdown was a signpost. What it pointed at was that the interaction is not happening at a point at all, that there is a heavy particle being exchanged, and that once you reach energies comparable to its mass, the theory changes character and the runaway stops. In 1983, at CERN's Proton-Antiproton Collider, the UA1 and UA2 collaborations found the W boson at about 80.4 giga-electronvolts and the Z boson at about 91.2. Carlo Rubbia and Simon van der Meer received the Nobel Prize the following year, the fastest award in the history of the prize. The particles sat almost exactly where the failure of the old theory said something had to appear. It is worth pausing on the shape of that reasoning, because it is going to matter when it fails. In every one of those four cases, the logic ran the same way. Step 1. Identify a quantity that is far smaller or far more finely balanced than the theory naively allows. Step 2. Refuse to accept the balance as a brute fact. Step 3. Ask what new object, entering with the opposite sign, would enforce the balance automatically. Step 4. Read the new object's mass off the size of the remaining discrepancy. Step 5. Go and look there, and notice the one weakness in that chain, which nobody had cause to worry about, while it kept working. Step 2 is not a deduction, it is a decision. In all four cases, the decision turned out to be correct, but its correctness was established by the discovery at the end, not by anything at the beginning. 4 successes in a row is a strong track record. It is not a proof, and there is nothing in the logic that says a 5th application must work. That is the whole of the difficulty we are walking toward, and I want it in your hands before we get there. 4 numbers that looked wrong. 4 times the wrongness was a message. 4 times the message named a particle, and 4 times the particle was found. So in the 1980s and 90s, when physicists looked at the Higgs mass and its 34 decimal places of cancellation, and concluded that something had to be waiting at the TV scale to do the cancelling, they were not speculating. They were applying, for the 5th time, the most reliable inference their field had ever produced. They designed a machine to go and look. The energy they chose was chosen because of that argument, and the argument told them exactly what kind of thing they should expect to find. Let us step back for a moment and put the pieces together. because we are about halfway through, and the argument has a shape worth seeing whole before we go on. We have a machine that cost something like $10 billion and ran for 17 years and found exactly one particle. We have that particle's mass, 125 gigaelectronvolts, and we have the fact that this number sits at the bottom of a cancellation 34 decimal places deep, with nothing in the theory to explain why. We have a criterion, naturalness, which says that a number like that is a message rather than an accident. And we have the reason physicists believed the criterion. 4 times before, an unnatural number had named a particle, and 4 times the particle had been found. So the question, going into the collider era, was not whether there was something new at the TeV scale. It was what the something was, and by the 1990s there was an overwhelming favorite. Supersymmetry is one of those ideas that sounds arbitrary until you see what it does, at which point it becomes very hard to let go of. The particles of the universe come in 2 families with completely different personalities. Fermions, quarks and electrons and neutrinos, have half-integer spin and refuse to occupy the same state as one another, which is the reason matter takes up space and the reason you do not fall through your chair. Bosons, photons, gluons, the W and Z, the Higgs, have integer spin and are perfectly happy to pile into the same state, which is the reason you can have a laser beam or a magnetic field. Matter is made of fermions. Forces are carried by bosons. The 2 families behave so differently that it is natural to think of them as separate kinds of thing. Supersymmetry proposes that they are not separate at all, that there is a symmetry of nature relating them, so that every fermion has a boson partner and every boson has a fermion partner, differing by half a unit of spin. The idea was developed in the early 1970s and given its 4-dimensional field theory form by Julius Wess and Bruno Zumino in 1974. The minimal version applied to the real particle content of the world, called the Minimal Supersymmetric Standard Model, was constructed by Savas Dimopoulos and Howard Georgi in 1981. Now here is what it does to the Higgs mass, and this is the whole reason anyone cared. Go back to that cancellation. The enormous contributions arriving from the top quark are negative. The enormous contributions arriving from the bosons are positive. Fermion loops and boson loops enter with opposite signs. That is not an assumption, it is a basic feature of quantum field theory. So if every fermion in the universe had a boson partner with the same mass and the same coupling strength, then for every enormous negative contribution, there would be an exactly equal and opposite enormous positive one. The catastrophic terms would not merely happen to cancel, they would be forced to cancel, by symmetry, exactly, with no tuning of any kind. The knife edge would disappear, because there would no longer be anything balanced on it. That is a beautiful solution. It is beautiful in the specific way that the 4 historical successes were beautiful. A suspicious balance is replaced by an enforced one, and the enforcement comes from the existence of new particles. Of course, we do not see those partners. There is no boson with the electron's mass. If there were, we would have found it in the 1930s. So supersymmetry, if it exists, must be broken. The partners must be heavier than their counterparts, and that means the cancellation is no longer exact. It becomes approximate, and the size of the leftover is set by how heavy the superpartners are. Push them up to the Planck scale, and you are back where you started, with a 34 decimal place problem. Keep them near the TeV scale, and the leftover is comfortably the size of the Higgs mass. That is the calculation that set the target. The superpartners had to be light, because if they were heavy, they solved nothing. And light, in this context, meant within reach of a machine that human beings could actually build. If that were all supersymmetry offered, it would be an interesting hypothesis. What made it the dominant framework of an entire generation is that it came with 3 additional gifts, none of which it was designed to provide. The first is unification. The 3 forces of the standard model have strengths that are not constant. They change with the energy at which you measure them. The strong force gets weaker at high energy. The electromagnetic force gets stronger. If you take the 3 measured strengths and extrapolate them upward, they converge toward each other and very nearly meet at a single point, somewhere around 10 to the 16th giga-electron-volts. Very nearly. They miss. But if you redo the extrapolation including the extra particles that supersymmetry requires, the 3 lines converge on a single point with remarkable precision. Ugo Amaldi, Wim de Boer, and Hermann Furstenau showed this in 1991, using precision data from LEP. It looks exactly like the fingerprint of a single unified force at very high energy, and supersymmetry produces it as a side effect of solving a completely different problem. The second gift is dark matter. In most versions of the theory, there is a conserved quantity called R parity, which has the consequence that the lightest supersymmetric particle cannot decay into anything, because there is nothing lighter for it to become, so it is stable. In many models, it is also electrically neutral and interacts only via the weak force. Stable, neutral, weakly interacting, massive. That is a description of dark matter. The theory was not built to explain dark matter. The candidate falls out of it for free. The third gift is the one that made physicists genuinely believe. If you take a stable particle with roughly weak-scale mass and roughly weak-scale interaction strength, and you ask how much of it would survive from the hot early universe as it expanded and cooled, the answer is not a wildly wrong number. The answer is approximately the amount of dark matter we actually observe. It comes out right to within a factor of a few, from a calculation involving nothing but the expansion rate of the universe and the strength of the weak force. This is called the WIMP miracle, and the word miracle is doing real work. Nobody arranged it. The energy scale that solves the Higgs problem is the same energy scale that gives you the right amount of dark matter. 3 independent problems: the fine-tuning of the Higgs, the unification of the forces, and the identity of dark matter, appeared to be solved simultaneously by one idea, and that idea also predicted that its evidence would appear at an energy human beings were about to reach for the first time. Tens of thousands of papers were written. Search strategies were designed. Detector components were specified with supersymmetric signatures in mind, the characteristic signature being a burst of jets accompanied by a large amount of missing energy, where the missing energy is the stable neutral partner walking out through the detector without leaving a trace. The scale of that theoretical effort is difficult to convey without sounding as though I am criticizing it, so let me just state it. Searching the physics preprint archive for supersymmetry in the title or abstract returns a body of work larger than the entire published output of many respectable physics subfields. Careers were made in it. Textbooks were written for it. Conferences ran on it annually for 4 decades, and none of that was unreasonable, because the alternative, assuming the balance was an accident and moving on, would have been a departure from the way physics had successfully worked for a century. I should also say what supersymmetry never claimed to do, since it is often overstated. It does not explain the values of the particle masses. In fact, it makes the counting worse. The minimal version introduces more than 100 additional free parameters of its own, and theorists spent a great deal of energy constructing simplified schemes to reduce them to a manageable handful. It does not explain the cosmological constant. If anything, it makes that problem harder, and it does not, by itself, contain gravity, though extending it to include gravity produces supergravity, and supersymmetry in some form is a requirement of every version of string theory. That last connection matters for the story, because it meant that a discovery at the collider would have been the first experimental foothold, however indirect, for the entire program of quantum gravity. There were other ideas, and it is only fair to name them. Technicolor proposed that the Higgs is not an elementary particle at all, but a composite object made of new, strongly interacting constituents, which removes the elementary scalar and therefore removes the problem entirely. Large extra dimensions proposed by Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali in 1998, and the warped geometry of Lisa Randall and Raman Sundram in 1999 dissolved the hierarchy in a different way. They proposed that gravity is not actually weak, but only appears weak because it leaks into dimensions we cannot see, so that the true fundamental scale is far lower than the apparent Planck scale, and the enormous gap that needs explaining is not there in the first place. That family of models predicted that the collider might produce microscopic black holes, which is where a certain amount of the public alarm around the machine originally came from. All of these ideas made the same basic promise: something new, at an energy the collider could reach, doing the job that the arithmetic said had to be done by something. There was one early warning sign, and in hindsight, the field could have taken it more seriously. Before the Large Hadron Collider, there was LEP, in the same tunnel, and LEP looked for superpartners too. It did not find any below about 100 giga-electron-volts. That was already mildly awkward, because the most natural versions of the theory had preferred them somewhat lighter. Theorists gave the problem a name, the little hierarchy problem, sometimes called the LEP paradox, and adjusted. The adjustment was reasonable in itself, but it established a pattern that would repeat. Every time the limits moved up, the acceptable amount of fine-tuning moved up with them, and the criterion that had originally motivated the whole search was quietly relaxed, rather than abandoned. The collider reached that energy in 2010. It ran for 16 more years. Now let me show you what it found. Nothing. That is the short version, and I am going to spend the next while making sure you understand exactly what kind of nothing it is, because the details matter enormously, and this is where careless summaries do the most damage. Start with the headline numbers. In the simplified models that experiments use as reference points, the ATLAS collaboration now excludes gluinos, the supersymmetric partner of the gluon, with masses below approximately 2.3 tera-electron-volts. Squarks, the partners of the quarks, are excluded below approximately 1.85 tera-electron-volts when the lightest neutralino is taken to be very light. The partner of the top quark, which is the single most important one because the top quark dominates the problematic contribution, is excluded up to roughly 1.2 tera-electron-volts. The CMS collaboration, working independently with a different detector, reports comparable limits. Gluinos approaching 2 tera-electron-volts, top squarks similarly around 1.2. Searches published through 2026, combining the full second run with part of the third, report the same finding in channel after channel. No significant excess anywhere in strong production. Beyond supersymmetry, the story is the same. No large extra dimensions. No microscopic black holes. Not one candidate event in 17 years. No technicolor resonance in the accessible mass range. No composite structure inside the quarks, or the electron down to the smallest distances probed. No leptoquarks. No fourth generation of matter particles. No heavy cousin of the Z boson in the searched range. The graviton resonances predicted by the warped extra-dimension models are now excluded above 4 tera-electron-volts in the simplest scenarios. Every specific thing that the naturalness argument suggested should be waiting at this energy has been looked for by 2 independent experiments, with a dataset 50 times larger than everything that came before, and none of it is there. It is worth understanding how a limit like that is actually produced, because it is not a matter of looking at a picture and seeing nothing. Physicists calculate, from the theory, exactly how many events of a particular shape a given particle mass would produce in a given amount of data. Then they count how many events of that shape they actually recorded, and they subtract their carefully modeled expectation from known standard model processes, which is by far the hardest part of the work. If the number they see matches the background expectation within its uncertainty, they can say, any new particle producing more than this many events is ruled out, because we would have seen the excess. Convert events into masses, and you get an exclusion. Every one of those 2.3 tera-electron-volt numbers is the end point of years of work by hundreds of people modeling backgrounds well enough to be confident that a signal is not hiding inside them. Now let me be scrupulous, because this is exactly the point where it is easy to overstate. An exclusion limit is not a proof of absence. Every one of those numbers I just quoted is quoted within a specific model, with specific assumptions about how the particle decays and what it decays into. Change the assumptions, and the limits change. If the superpartners are close in mass to one another, what physicists call a compressed spectrum, then the decay products are soft and low in energy. They look like ordinary background, and the detector's trigger system may never have selected the event in the first place. If the new particle is long-lived, it may travel meters before decaying, or leave the detector entirely, and the standard searches were not designed to see that. If R parity is not conserved, the missing energy signature that all of this was built around simply does not occur, and the limits weaken substantially. There is one more honest caveat, and it unsettles people when they first hear it. The collider does not record most of what it produces. Bunches of protons cross 40 million times a second, and each crossing produces dozens of collisions, and there is no storage system on Earth that could write all of that down. So the experiments use a trigger, a layered system of hardware and software that decides, in a few millionths of a second, whether an event is interesting enough to keep. Well over 99.9% of collisions are discarded permanently, within microseconds, and are gone forever. The trigger was designed by people who had an idea of what they were looking for. If nature produced something that did not resemble any of the signatures anticipated in advance, it is entirely possible that the collider made it, many times, and threw it away. Physicists know this perfectly well, which is why a great deal of recent effort has gone into broadening trigger strategies and into so-called data scouting techniques that keep reduced information about far more events. But it remains true that the searches were shaped by expectations, and the expectations were shaped by naturalness. So supersymmetry is not dead. I want to say that clearly, because you will hear people say it is, and they are being imprecise. Supersymmetry, as a possible symmetry of nature, is alive and cannot be killed by any finite experiment. What is dead is something narrower and far more consequential. What is dead is the version of supersymmetry that solved the naturalness problem. That version required the superpartners to be light. That was the whole point, because the residual tuning is set by their mass. At 2.3 tera-electron-volts for the gluino, the cancellation is no longer clean. You are back to requiring a fine adjustment, smaller than before, but still a fine adjustment, of perhaps 1 part in 100 or 1 part in 1,000, depending on the model. The theory can survive. It just cannot do the job it was hired for. That distinction is the whole story of the last 15 years, and if you take away one thing tonight, I would like it to be that one. The collider did not falsify supersymmetry. It falsified the reason for believing in supersymmetry. There is a way of measuring the damage numerically. If you take the fine-tuning measure that Barbieri and Giudice introduced, and you evaluate it for supersymmetric models that survive the current limits, you find that the models require tuning at the level of a fraction of a percent, a cancellation of 1 part in several hundred or worse. Compare that to what the theory was supposed to achieve, which was no tuning at all. Then compare it to the problem it was invented to solve, which was 1 part in 10 to the 34th. Supersymmetry at these masses has improved the situation by 31 or 32 orders of magnitude and left 2 or 3 unexplained. That is either a magnificent partial success or a solution that no longer solves anything, depending entirely on whether you think a residual tuning of 1 in 1,000 requires an explanation. And notice, that is the same judgment call we ran into before. There is no measurement that settles it. And then there is the other front, because the collider was never the only instrument looking. If the lightest superpartner is dark matter, then it is not only being produced in Geneva, it is streaming through you right now. The direct detection experiments are among the strangest and most beautiful machines ever built. The idea is straightforward. Fill a tank with something very heavy and very pure. Liquid xenon is the current favorite. Bury it deep enough that the rock above filters out cosmic rays. Shield it obsessively, cool it, and then wait for a dark matter particle to strike a single xenon nucleus and make it recoil. The signal is a flash of light and a few electrons. The background is everything else in the universe. Natural radioactivity in the tank walls, in the rock, in the xenon itself, in the dust that settled during assembly. These experiments have been run in a mine in South Dakota, under a mountain in Italy, in a tunnel in China, in a nickel mine in Ontario. Over about 20 years, these detectors have scaled from kilograms of target material to multiple tons, and their sensitivity has improved by something like 6 orders of magnitude. That is one of the steepest experimental improvement curves in the history of physics. They have found nothing. In December 2025, the Lux Zeppelin experiment, running under the Black Hills of South Dakota, reported new world-leading limits, closing off further regions of parameter space, including candidate masses, between 3 and 9 giga-electronvolts. The classic weakly interacting massive particle, the WIMP that the miracle pointed to, has now been excluded across most of the parameter space where the miracle worked. And in the same result there was something else, which is genuinely remarkable, and also quietly ominous. For the first time in that detector, they saw solar neutrinos. Neutrinos produced in the core of the Sun, arriving at the tank and scattering coherently off entire xenon nuclei at a confidence level of 4.5 standard deviations. That is a beautiful measurement in its own right. It is also a warning, and the physicists involved described it as one. Neutrinos scattering off a nucleus and dark matter scattering off a nucleus look almost identical. As the detectors get more sensitive, they begin to see a background of neutrinos from the Sun, from cosmic rays hitting the upper atmosphere, from supernovae across the universe. That background is called the neutrino fog, and once you are inside it, improving your detector no longer straightforwardly improves your search, because every gain in sensitivity brings in more neutrinos alongside any dark matter signal. The fog is not a wall. You can push through it with enough exposure and clever directional techniques. But the era in which each new detector generation could simply be built bigger and gain orders of magnitude is coming to an end. So this is the position. The collider looked at the energy the argument specified and found nothing. The underground detectors looked for the same physics from a different direction and found nothing, and are now beginning to run out of room in which to look at all. The map has been filling in, region by region, for 15 years, and every region has come back white. Except, and this is where it gets painful, twice it did not. Twice something appeared. And I want to tell you about both, because what happened next tells you more about this field than any exclusion plot ever could. On the 15th of December 2015, in the main auditorium at CERN, 2 collaborations presented their first results from the newly upgraded collider, and for about 8 months, a substantial fraction of the world's theoretical physicists believed the desert had ended. Let me put you in that room. The auditorium is full, and there are people standing along the walls. It is a routine end-of-year seminar. The machine has only been running at the higher energy for a few months, and nobody is expecting a discovery. The Atlas speaker is working through the standard sequence of plots, one search channel after another, all of them agreeing with expectation. Then the diphoton spectrum comes up, the number of events in which the collision produced two photons, plotted against the combined mass of those two photons. It should be a smooth curve, falling steadily. It is a smooth, falling curve, except at 750 giga-electron-volts, where it is not. There is a bump. It is not enormous. It is the kind of thing that appears and vanishes routinely, but the room has done this arithmetic before and knows what a 3.9 standard deviation local excess looks like, and there is a particular quality to the silence. Then CMS presents. Different detector, different collaboration, different people, no communication permitted. And in the CMS diphoton spectrum, there is a bump at 750 giga-electron-volts. That is the moment. Two independent instruments, forbidden from consulting each other, seeing something at the same mass. That is precisely the pattern that the Higgs discovery had shown 3 years earlier. People in that auditorium started doing calculations on their phones before the questions had finished. What happened next was one of the fastest collective responses in the history of theoretical physics. Within a week, dozens of papers had appeared on the preprint server. Within a month, hundreds. Over the 8 months that followed, roughly 500 theoretical papers were written, attempting to explain a bump at 750 giga-electron-volts. They proposed extended Higgs sectors, heavy axion-like particles, composite resonances, radions from extra dimensions, states from string constructions, dark matter mediators. Some of these papers were extremely good. Many were written by people who knew exactly how likely it was to be a fluctuation, and wrote them anyway. Because if it were real, the first paper with the right explanation would be one of the most important papers of the century. With the full 2016 dataset, the excess disappeared, completely. Not reduced, not shifted, gone, absorbed back into a perfectly smooth falling curve, exactly as a statistical fluctuation does. The collaborations announced it at a conference in Chicago in August 2016. I want to stay with this a moment longer than the physics strictly requires, because the physics is not the interesting part. The physics is that a spectrum has many bins, and some bin will fluctuate high. That is why the field demands 5 standard deviations, and why it corrects for the look elsewhere effect, which pulled that 3.9 sigma down to around 2.1 before anyone got excited. The interesting part is what those 8 months cost. 500 papers is not an abstraction. Postdoctoral researchers on 2-year contracts, whose entire future depends on what they publish before the contract ends, dropped what they were doing and worked on this. Graduate students changed thesis topics. Groups reoriented. And all of that work was careful, competent, honest physics, genuinely good calculations, correctly done, about an object that did not exist. There is no error anywhere in that story. Nobody was foolish. The response was entirely rational, given the information available, and the information was noise. The 5 standard deviation threshold exists because of episodes exactly like this one. 5 sigma corresponds to roughly a 1 in 3.5 million chance that a fluctuation this large or larger would occur in one direction by accident. That is an absurdly conservative bar by the standards of most sciences, where 3 sigma, or even 2, is often treated as a result. Particle physics adopted it not out of fastidiousness, but out of experience. The field performs an enormous number of implicit comparisons, many channels, many mass bins, many selection criteria, many experiments, and under those conditions, 3 sigma effects appear and evaporate at a rate that would embarrass anyone who published on them. The threshold is institutional memory, encoded as a number. and the 750 giga-electron-volt episode demonstrates that even a field which knows this perfectly well, and which had corrected the significance downward itself before anyone got carried away, still could not stop 500 papers from being written. That is what it is like to want an answer very badly for a long time. Not stupidity, not credulity, just an enormous number of intelligent people correctly calculating the consequences of something that was not there. It also was not the first time, and it will not be the last. In 2011, the Opera experiment in Italy announced that neutrinos had arrived from CERN faster than light should have permitted. It made headlines everywhere. The collaboration, to its enormous credit, had presented the result explicitly as a request for scrutiny rather than a claim, because they could not find the mistake themselves. The mistake was found within months. A fiber optic cable that was not fully seated, and a clock oscillator that was running slightly fast. 2 pieces of hardware, worth a few $100s between them. There have been others, measurements of the proton's radius that disagreed with each other, ratios in the decays of B mesons that appeared to violate a symmetry between electrons and muons for several years before better analyses pulled them back into line. A measurement of the W boson mass from Fermilab in 2022 that sat 7 standard deviations from expectation and has not been confirmed by anybody else. Each of these was, for a while, a candidate for the crack in the wall. Each of them closed. And then there was the muon, which was the other one, and which lasted 25 years. A muon is a heavy electron, about 200 times the mass, and like an electron, it behaves as a tiny magnet. Quantum theory predicts the strength of that magnetism with extraordinary precision, but the prediction includes a contribution from every particle that can briefly appear around the muon and vanish again, including particles nobody has ever discovered. So if you measure the muon's magnetism precisely enough and compare it to the calculation, any disagreement is a direct measurement of the existence of something unknown. It is one of the most elegant experimental ideas in physics, a way of weighing the undiscovered contents of the universe by watching a single particle wobble. Brookhaven National Laboratory measured it and, in 2001, and again in 2006, reported a disagreement with the calculation. It was not large enough to claim a discovery, but it would not go away. For 2 decades, it was the best surviving quantitative hint that something beyond the standard model existed, and a great deal of theoretical work was built on top of it. Fermilab took over the measurement, which required physically transporting the 15-meter superconducting storage ring from Long Island to Illinois, 3,200 miles by barge around Florida and up the Mississippi, then by truck at night down closed highways, over 35 days in 2013, because the ring could not be flexed by more than a few millimeters without destroying it. People came out to watch it go past. Fermilab's results came in 2021, 2023, and finally on the 3rd of June, 2025. The final measurement reached a precision of 127 parts per billion, beating its own design target of 140. It is one of the most precise measurements of anything ever made, and the anomaly is gone. It did not go away because the measurement changed. The measurement is superb, and it agrees with Brookhaven. It went away because the prediction moved. The hardest part of calculating the muon's magnetism is a contribution involving the strong force, which cannot be computed with the usual approximation methods and had traditionally been estimated using measurements from electron-positron colliders. Over the last several years, a different approach, lattice quantum chromodynamics, in which spacetime is approximated by a grid and the calculation is done by supercomputer, became precise enough to compete. In 2025, the Muon G2 Theory Initiative adopted a consolidated lattice average, and the standard model prediction shifted upward, to 116,592,033 in the units the field uses, with an uncertainty of 530 parts per billion. The new prediction disagrees with the old prediction at about 3 standard deviations, and it agrees with the measurement. So the last great anomaly in particle physics was not killed by an experiment, it was killed by a recalculation. 25 years of the most tantalizing number in the field, and it turned out that the theory had been slightly wrong about itself. There is a loose end. The lattice result sits uncomfortably with 4 decades of collider data used in the older method, and that tension is a real open problem. But nobody can now describe the muon as strong evidence for new physics. 2 hopes, both gone, and with them, the last thing standing between the field and a word it had been avoiding for 30 years. The word physicists use, among themselves, is nightmare. I find it remarkable that they named it in advance. Somewhere in the 1990s, while the tunnel was being cleared and the magnets were being designed and the budgets were being argued through national parliaments, the community sat down and worked out what the range of possible outcomes was, and gave the worst one a name. That is an unusual thing for any group of people to do about their own life's work. Most of us do not name the version of the future in which our central assumption turns out to be wrong. Physicists did, and then they built the machine anyway, and then they got the outcome they had named. The nightmare scenario is not that the collider explodes, or that the funding is cut, or that a rival finds the answer first. The nightmare scenario is that the machine works perfectly, runs for its full lifetime, collects all its data, and finds the Higgs boson and absolutely nothing else. That is the outcome the field named in advance, decades ago, as the worst thing that could happen, and it is, as closely as anyone can tell, what happened. Which brings us back to that stretch of unexplored energy I mentioned earlier, and to what it looks like now. Between the electroweak scale, where the Higgs lives, and the Planck scale, where gravity becomes strong, there are 16 orders of magnitude. When I first described that gap, it was a hypothetical. The thing naturalness was invented to rule out, the possibility nobody wanted to plan for. It is not hypothetical now. The collider has looked at the bottom of that gap, the only part of it any instrument can reach, and the bottom is empty. 16 orders of magnitude, of nothing, is no longer the fear. It is, as far as anyone can currently demonstrate, the measured landscape. And I want to be honest that we have only examined the first small step of it. The collider probes to a few tera-electron volts. The Planck scale is at 10 to the 19th. In terms of the ground we would need to cover, we have walked out of the car park. But the argument was never that new physics was somewhere in that range. The argument was that it had to be near the bottom, close to the Higgs, because the further away it sits, the less it helps. The part of the desert that mattered is precisely the part we have crossed. I should be careful here to separate 2 very different kinds of nothing, because they get conflated constantly and the difference matters. The first kind is the absence of new particles at the collider, which is a measured, quantified, published result with error bars. The second kind is the claim that the desert extends all the way to the Planck scale, which is not a result at all, but an extrapolation, a statement about 16 orders of magnitude on the basis of having examined the first one. Nobody has measured the desert. What has been measured is that the specific region where the argument said the answer had to be is empty. Those are different statements, and only the first one is evidence. So what does a discipline do when its central organizing expectation fails? 3 things, and all 3 are happening simultaneously, and the disagreement between them is genuinely the most interesting thing in fundamental physics right now. The first response is to keep the theory and drop the motivation. In 2004, Nima Arkani Hamed and Savas Dimopoulos proposed what they called split supersymmetry. The idea is straightforward and slightly shocking. Accept that the Higgs mass is fine-tuned, stop trying to explain it, and keep supersymmetry anyway for its other virtues. Push the scalar superpartners up to enormous masses, far beyond any conceivable experiment, and keep only the fermionic partners light enough to preserve gauge unification and provide a dark matter candidate. This is entirely coherent physics. It is also, by explicit construction, a theory that abandons the problem it was invented to solve. The authors were completely open about this. They were pointing out that if the universe is fine-tuned anyway, and there is at least one number, the cosmological constant, where it appears to be tuned to something like 1 part in 10 to the 120th, then adding one more tuning to the ledger is not the disaster it once seemed. The second response goes further and tries to explain the tuning rather than accept it. If there is not one universe but an enormous number of regions with different low-energy physics, then every value of every parameter is realized somewhere, and the question of why we observe these particular values has an answer. Because most values do not permit observers. In a region where the Higgs mass sits far from its actual value, there are no atoms, no chemistry, no structures capable of asking questions. We measure 125 giga-electronvolts because we could not have measured anything else and still been here. String theory supplied a possible mechanism for this. The theory's extra dimensions can be folded up in a huge number of ways, and each folding gives different low-energy physics. Raphael Bousso and Joseph Polchinski analyzed the counting in 2000, and the figure that entered the literature, 10 to the 500th possible vacuum states, is not a measurement, but it conveys the scale of the idea. In 2003, Leonard Susskind wrote an essay called The Anthropic Landscape of String Theory that made the argument explicit, and the field has been arguing about it ever since. The strongest thing that can be said for this reasoning is that it has worked once, spectacularly. In 1987, Steven Weinberg argued that if the vacuum energy of the universe were much larger than a certain value, galaxies would never have formed, because the expansion would have pulled matter apart before gravity could gather it. So any universe containing observers must have a vacuum energy below that bound, and the most likely value is somewhere near it rather than at zero. At the time, the measured value was consistent with zero, and most physicists expected it to be exactly zero for some reason yet to be discovered. In 1998, two teams observing distant supernovae found that the expansion of the universe is accelerating, driven by a vacuum energy that is small, positive, and in the general vicinity of Weinberg's bound. That is the single most successful anthropic prediction in the history of physics, and everyone who takes the landscape seriously points to it. The strongest thing against it is equally clear. It is extremely difficult to turn into a prediction you could check. If the parameters vary across regions we cannot observe, and we necessarily find ourselves in a region compatible with our existence, then almost any measurement is compatible with the framework. A framework that can accommodate anything forecasts nothing. The third response is the most radical and the hardest to argue with. It says that naturalness was simply the wrong criterion, and that the Higgs mass requires no more explanation than any other number in the theory. Nobody demands an explanation for why the electron is roughly 1/1836th the mass of the proton. It is a measured ratio. It is what it is. On this view, physics spent 40 years and a very large amount of money answering a question that the universe had never posed, and the collider's result should be read not as a failure to find the answer, but as the discovery that there was no question. There is a fourth position too, quieter than the others, which holds that the answer exists and is simply somewhere nobody thought to look. New physics may be light rather than heavy, and feeble rather than strong. A particle that interacts far more weakly than the weak force would be produced only rarely, and would have slipped through every search built around the assumption that new particles are heavy and produced copiously. This idea has become the fastest growing search program in the field. There is now a detector called phaser sitting in a service tunnel 500 meters down the beamline from one of the collision points, looking for particles that travel that far before decaying. There are proposals for detectors on the surface above the collision halls, watching for something that emerges from the rock. Searches for long-lived particles, dark photons, axions, and sterile neutrinos have expanded enormously in the last decade. This is a genuine strategic shift, and it is the one concrete good the null result has already produced. The field stopped assuming it knew what it was looking for. That view has been argued in public for 2 decades. Peter Voigt's book, Not Even Wrong, and Lee Smolin's The Trouble with Physics, both published in 2006, made the case that the field had lost contact with experiment. Sabine Hossenfelder's Lost in Math, in 2018, made a sharper and more specific version of it, that physicists had been selecting theories by criteria of beauty, elegance, and naturalness, and that these criteria have no track record of identifying true theories and considerable evidence of misleading people. The response from inside the field has been more thoughtful than the caricature suggests. Nima Arkani Hamed, who has spent much of his career building natural theories, has argued publicly that the failure of naturalness may be the most important experimental result in decades, precisely because it does not falsify one model but a way of thinking, and results that falsify ways of thinking are rarer and more valuable than results that falsify models. That is not a defensive position. That is somebody taking the loss seriously. So the field now contains, simultaneously, people who think the answer is at higher energy, people who think it is at lower energy but weaker coupling, people who think the tuning is environmental and explained by our own existence, and people who think there was never anything to explain. These are not fringe positions against a consensus. There is no consensus. That is the situation. And in the middle of that, in May of this year, they voted to build another one. On the 22nd of May, 2026, 5 weeks before the last beam, the CERN Council met in a dedicated session in Budapest and updated the European strategy for particle physics. The process behind that meeting had taken more than 2 years. It began in March 2024 and drew on more than 260 written submissions from the community, and the conclusion was unanimous. The Council confirmed completing the high luminosity upgrade as Europe's highest medium-term priority, and then recommended, as the preferred next flagship project, an electron-positron collider called the Future Circular Collider. Let me tell you what they voted for. Picture a ring, 90.7 kilometers in circumference. Not 27, 90. It would run under the French-Swiss border, beneath farmland and suburbs and villages and the edge of Lake Geneva, at depths between 200 and 400 meters. It would be reached through 8 surface sites and would house 4 experiments in 4 caverns. The layout was not chosen casually. Engineers developed and analyzed 100 different scenarios for where to put it, weighing the physics against geology, groundwater, protected land, and the willingness of the people who live above it. Come down into it with me for a moment, because it is worth feeling as a physical object rather than a budget line. You are standing in a tunnel 300 meters beneath a hillside in eastern France. It is perfectly circular in cross-section, wide enough to drive a small vehicle through, and it is lit at intervals by fixtures that recede in both directions until they converge. The floor is level to within a few millimeters over its entire length, because the beam does not tolerate slopes it has not been told about. Behind you, the tunnel curves away so gently that it looks straight, and it stays looking straight for as far as you can see, and if you started walking in that direction at a comfortable pace, you would arrive back at this exact spot in about 18 hours, having passed under 2 countries, 1 lake, a mountain range, and several 100,000 sleeping people. In the beam pipe beside you, If this were finished, electrons and their antimatter partners would be circling in opposite directions, meeting at 4 points, producing Higgs bosons at a rate of something like one every few minutes for 15 years. What it would produce over a 15-year program is worth stating, because the numbers explain the strategy. Around 6 million Z bosons, around 240 million pairs of W bosons, around 2.7 million Higgs bosons, around 2 million top-antitop pairs. The current collider produces Higgs bosons buried in an overwhelming mess of strong force debris. An electron-positron machine produces them in clean, quiet events where essentially everything in the collision is understood. It is the difference between studying a bird in a hurricane and studying it in a room. The estimated construction cost of that first stage is 15.3 billion Swiss francs, spread over roughly 15 years starting in the early 2030s. The decision is targeted for 2028. If approved, first operation would come in the mid-2040s, when the current machine's program ends in 2041, and then, if all of that happens, a second machine in the same tunnel, a proton collider running at 85 tera-electron volts, 6 times the current energy, entering operation in the early 2070s. Read those dates again. A physicist who is 30 years old today would be around 50 when the first stage produced data, and would be approaching 80 when the second stage turned on. Most of the people who vote on this, design it, and fight for its funding will not see the end of it. They are building an instrument for people who have not been born. And here is the detail I find most telling of all, the one that shows how much the last 15 years have changed this field. Read how they are justifying it. When the current collider was sold to governments in the 1990s, the language was about discovery, new particles, new forces, the next layer of reality. The naturalness argument was in the background of every one of those documents, saying that something had to be there. The language now is different. CERN's Director General, Mark Thompson, framed the case around ultra-precise measurement of the Higgs boson and the other known particles. Carl Jacobs, who served as secretary of the strategy process, described the machine as offering the world's broadest high-precision program. John Ellis, a theorist who has been at the center of this field for half a century, put the remaining prize like this: is the Higgs boson really what it seems? Not what else is out there. Is the thing we found actually what we think it is? That is a profound shift, and it is a mature one. The argument is no longer that we know something is there and need a bigger net. The argument is that we have exactly one elementary scalar particle in the universe. We have measured its properties to a few percent, and at a few percent we would not notice if it were subtly different from the standard model prediction. Measure its couplings to a fraction of a percent, measure how it interacts with itself, and any deviation would point toward whatever is out there without ever producing it directly. There is precedent for that strategy working. LEP, in this same tunnel, never had enough energy to produce a top quark, but by measuring other quantities precisely enough and accounting for the top quark's contribution to those quantities as a virtual particle, LEP predicted its mass to within a few percent before Fermilab observed it in 1995. Precision found the top quark before energy did. Now, I would be doing you a disservice if I did not stop here and deal directly with the objection that is probably forming, because it is the reasonable objection and it deserves a real answer rather than a dismissal. Before I get to it, let me clear away the other objections that circulate about this machine, because you have almost certainly encountered them and they deserve a straight answer. The first is that the collider is dangerous, that it might create a black hole that consumes the Earth, or a form of matter that converts everything it touches, or a collapse of the vacuum itself. This was taken seriously and examined formally before startup, in safety reviews published in 2003 and 2008, and the decisive argument is beautiful in its simplicity. Cosmic rays, with energies far exceeding anything the collider produces, have been striking the Moon, the Sun, white dwarfs, and neutron stars continuously for billions of years. The number of such natural collisions that have occurred in the observable universe exceeds everything the collider will ever produce by an enormous factor. Those objects are still there. If collisions at these energies destroyed astronomical bodies, there would be no astronomical bodies, and there would be no one here to worry about it. Beyond that, any microscopic black hole capable of forming would evaporate essentially instantly, and even setting that aside, the collision products carry momentum and would not stay gravitationally bound to the Earth in the first place. The second is that the machine has altered reality. The claims connecting it to shifted memories, to dimensional doorways, to a date on which something in the world quietly changed. There is no mechanism, in any tested or seriously proposed physics, by which a particle collision, however energetic, edits memory or history. Collisions at these energies happen naturally in the upper atmosphere, many times every second above your head. The phenomenon of large groups of people confidently misremembering the same detail is well documented in cognitive psychology as ordinary reconstructive memory error, and it has been studied in populations who have never heard of particle physics. Memory is not a recording, it is a reconstruction, rebuilt slightly differently each time it is used. That is a genuinely strange fact about being a person, and it does not require a collider to explain it. The third objection is the serious one, and I want to give it a proper answer. 15 billion francs, on top of $10 billion, for a question that has not been answered. Is this simply money being poured into a hole in the ground? Here is the honest case, in 3 parts. The first part is that a negative result is a result. The exclusion of natural supersymmetry at the tera-electron-volt scale is one of the most consequential experimental findings of this century, precisely because it constrains what can be true. 40 years of theoretical possibility have been converted into knowledge. That is not nothing. It is uncomfortable, which is a different thing. The second part is the Higgs itself. A mechanism proposed in 1964 was confirmed in 2012. Human beings predicted the existence of a field filling all of space on the basis of mathematics, and then built a machine to check, and were right. The third part is the one that gets overused, so let me use it carefully. The World Wide Web was invented at CERN in 1989 by Tim Berners-Lee to solve the problem of physicists in different countries being unable to find each other's documents. Accelerator physics feeds directly into cancer treatment. There are hospitals today treating tumors with proton and carbon ion beams using technology developed for particle experiments. Detector physics feeds into medical imaging. All of that is true, but no honest defender should claim the collider was built for the spin-offs, and I will not. It was built to answer a question. The uncomfortable truth is simply that it answered a different question than the one it was pointed at, and the answer it gave is one the field is still absorbing, because it is not an answer about particles at all. So let us go back to the question, now that you have everything you need to see what actually happened to it. Why is the Higgs boson light? That was the question. $10 billion, 17 years, 10,000 careers, 2 continents, 1 cancelled machine under a Texas field, and 1 completed machine under a Swiss border. And the honest answer, tonight, is that nobody knows. But I have been withholding something from you all evening, and this is where I have to hand it over. Because the reason nobody knows is not the reason you would expect. It is not that the machine was too small. It exceeded its own performance targets by nearly a factor of 2. It is not that nobody looked hard enough. 2 independent collaborations, several thousand people each, spent 17 years and produced 50 times the combined output of every Hadron Collider before them. It is not that the theorists were lazy. Tens of thousands of papers, 4 decades, some of the best minds of 2 generations. The reason there is no answer is that the field can no longer agree there was a question. I want to lay that out very carefully, because it is the whole thing. Naturalness, the principle that sent everyone looking, that set the machine's energy, that shaped which searches were designed, and which triggers were written, and therefore which collisions were kept, and which were thrown away forever, was never a law of nature. It was a criterion for deciding which numbers demand an explanation. No experiment ever tested it. No theorem ever required it. It was adopted because it had worked 4 times, and 4 successes in a row is the best evidence any working scientist ever gets, and it is still not the same thing as a proof. And here is the position the field is now in. Consider the 2 possibilities. Possibility 1. Naturalness is correct. The Higgs mass really does demand an explanation, and the explanation exists at an energy we have not reached. In that case, the collider did not fail. It simply did not go far enough, and a bigger machine would find the answer, and everything about how physics has been done for a century remains intact. Possibility 2. Naturalness was the wrong criterion. The Higgs mass is 125 giga-electronvolts, in the same way that the electron is roughly 1/1836th the mass of the proton. As a fact, not as a puzzle. In that case, there was never anything to find, and 40 years of work went into a question that the universe had not asked. Both of those possibilities are entirely respectable. Both are held by serious people who understand the data completely. And notice that the disagreement between them is not about any measurement. Everyone agrees the Higgs is at 125 giga-electronvolts. Everyone agrees the quantum corrections go as the square of the cutoff. Everyone agrees on every exclusion limit, to the last decimal place. The entire dispute is about whether the resulting arithmetic constitutes a problem. Now tell me which experiment distinguishes those 2. Take your time with it. If the new collider finds a particle in 2045, possibility 1 is vindicated. Wonderful. But suppose it does not. Suppose the future circular collider runs for 15 years and finds nothing beyond exquisitely precise measurements of things we already know about. Does that establish possibility 2? It does not. It is entirely consistent with possibility 1 being true at an energy just above the new machine's reach, and then the same argument would apply to the machine after that, and to the machine after that, forever. No finite sequence of null results can ever establish that a question was malformed, and no discovery, however wonderful, can retroactively establish that the criterion was sound rather than lucky. Physics has been in hard places before, and it is instructive to notice how different this one is. When the ultraviolet catastrophe broke classical physics at the end of the 19th century, there was a measurement that did not fit. Hot objects did not glow the way the equations said they should, and Planck solved it in 1900. When the orbit of Mercury refused to behave, there was a number, 43 arcseconds per century, sitting there waiting for somebody to explain it, and Einstein explained it in 1915. When the photoelectric effect misbehaved, there was data. Every previous crisis in physics came with a disagreement between a measurement and a prediction, and disagreements of that kind, however hard, at least tell you when you have solved them. This one has no disagreement in it anywhere. There is no measurement that the standard model gets wrong at the collider. Not one. The crisis is entirely on the side of expectation, and expectation is the one thing an experiment cannot weigh. That is not a temporary difficulty awaiting better technology. It is structural. There is no measurement, in principle, that adjudicates between a hard problem and a badly posed one. That is why the most expensive question in modern physics still has no answer. Not because we lacked the instrument. We built the instrument, and it worked beautifully. Because the community that asked it can no longer agree that it was a question. There is a version of this that is even less comfortable, and it is worth stating because some physicists hold it seriously. It is possible that both possibilities are true at once, that naturalness is a perfectly good criterion, that the Higgs mass genuinely does have an explanation, and that the explanation lives at an energy no civilization on a planet will ever reach. A collider capable of directly probing the Planck scale, built with anything resembling the magnet technology we have, or can foresee, would need a circumference on the order of the solar system. That is not an engineering challenge. That is a statement about the size of the thing we live on. If the answer is up there, it is not hidden. It is simply out of reach, permanently, and the universe is under no obligation to place its explanations within the budget of the beings who want them. And I want to name the callback I have been carrying since the middle of tonight, because it has changed meaning without anyone announcing it. 16 orders of magnitude of nothing. When I first said that phrase, it was the nightmare, the thing naturalness had been invented to rule out, a possibility so unwelcome that the field had given it a name in advance and hoped never to use it. It is not a nightmare anymore. It is a working description, not proven, not measured across its full span, but no longer the outcome anyone is planning against. In one human generation, the desert went from the thing physicists were afraid of to the landscape they are learning to live in. That transition happened quietly, in review articles and conference talks and adjusted expectations, and it is one of the largest changes in the intellectual furniture of physics since the 1930s, and almost nobody outside the field noticed it happening. I said at the start of tonight that the collider found exactly one thing. That was not quite true, and I want to correct it now. It found exactly one particle, but it found a second thing, and the second thing is not made of matter, and does not have a mass, and will never appear on an exclusion plot. What it found is that our sense of which numbers require explaining is not itself reliable. That the criterion by which physicists had decided, for 4 decades, what counted as a mystery and what counted as merely a fact, was a habit of mind that had happened to work 4 times, and was now being asked a 5th time and returning something nobody knew how to read. The knife edge, by the way, has not moved. That is the part I keep coming back to. Nothing about the physics changed on the 4th of July 2012, or on the 27th of June this year. The enormous contributions still arrive. They still cancel to something like 34 decimal places. The residue at the bottom of that cancellation is still the number that decides whether atoms can exist, and therefore whether you can exist, and it is still balanced there tonight while you are lying in the dark listening to this. Every atom in your body is sitting on that balance right now. What changed is not the universe. What changed is that physicists no longer agree that the balance needs an explanation. I find that genuinely one of the strangest results in the history of science. They built the largest machine that has ever existed to interrogate the vacuum, and the vacuum declined to answer, and what came back instead was information about the people asking. It is worth sitting quietly for a moment with what is actually down there tonight, because it is a strange kind of stillness. 27 kilometers of tunnel, 100 meters under vineyards and roundabouts, and a runway, and a lake, lit and empty. The magnets are still cold. They are kept cold, because warming them and cooling them again takes months and costs a fortune. So for 4 years, they will sit at 1.9 Kelvin in the dark with nothing passing through them. Above them, at this hour, people are asleep in Saint-Genis and Ferney-Voltaire and Meyrin, and almost none of them think about it, in the same way that almost none of us think about the water mains. In the caverns, the detectors are being opened up, layer peeled back from layer, by people in hard hats working from scaffolding inside instruments the size of cathedrals. And somewhere in that machine, there are still surfaces that have never been touched by air since they were sealed 20 years ago, holding a vacuum emptier than the space between the planets, waiting. And I want to say clearly, because it would be easy to hear all of this as a story about failure, that I do not think it is one. This is what science looks like when it is working properly and the news is bad. A field made a specific, falsifiable commitment. It spent enormous resources testing it. The test came back negative, and it published the negative result, and it is now arguing in public about what the negative result means, and nobody is pretending. There are disciplines that could not have survived this. Physics is metabolizing it, slowly and awkwardly and honestly, in front of everyone. There is also a real hope in what comes next, and I do not want to leave you without it, because it would be a distortion. The strategy has changed, and the new strategy has a better track record than people assume. Precision has found things before energy did. LEP never made a top quark, and predicted its mass anyway, by measuring other quantities carefully enough that the top quark's invisible contribution could be read off the discrepancy. That is the plan now. Measure the Higgs boson's interactions to a fraction of a percent. Measure how it couples to itself, which is the one place where the shape of the field filling all of space could still turn out to be different from what the theory assumes. If there is anything out there at all, heavy and rare, or light and feeble, it leaves fingerprints on those numbers, whether or not any machine can produce it directly. It is a slower, quieter, less cinematic way to look for the unknown, and it may well work. There is one more thing I want to leave with you, and it is the reason I wanted to tell you this story at all. Every single one of us walks around holding a private version of naturalness. You have a list, you did not write it down, and you have never examined it, of the things in your life that require explanation, and the things that are simply how it is. Why your friend has not called, that goes in the first column, and you turn it over at 2 in the morning. Why the sky is the color it is, second column, and you have never once wondered. Why one relationship worked and another did not. Why that opportunity came to you and not to somebody else. Why one relationship worked and another did not. Why one relationship worked and another did not. Why one relationship worked and another did not. Why one relationship worked. Each of those gets sorted instantly, without deliberation, into needs explaining or just is. It is a habit assembled out of your history and the things that happened to work before. The most rigorous discipline our species has ever built made that same sort of judgment, wrote it down carefully, tested it with the most powerful instrument in history, and discovered that it could not tell whether the judgment had been right. If they cannot check theirs, with all of that, then it is worth being gentle with yourself about yours. The machine under the border is quiet tonight. In 4 years, it will start again, more powerful than before. Somewhere around 2045, if the votes go the way the votes went in Budapest in May, a longer ring will begin its own attempt on the same question, and the people who turn it on will mostly not be the people who approved it. That is a species that keeps asking, without any guarantee whatsoever that the thing it is asking about is a question. I do not know a better description of us than that. Thank you for spending this time with me, walking out into the desert and coming back with nothing but a much better understanding of the emptiness. If a slow walk through a beautiful failure is the kind of thing you like falling asleep to, a like or subscribe would mean a great deal. It genuinely helps me keep making these. And remember, the next time you catch yourself asking why something in your life turned out the way it did, that the hardest part was never finding the answer, it was deciding the question was worth asking. Good night, and may you never look at an unexplained number quite the same way again.